Hello everyone, my name is Jamil and today I'm gonna be talking about how to apply ODE for calculating degradation rate of a nuclear industry. So, what is ODE? Ordinary differential equation is referred to as ODE. It is a mathematical idea that is used to explain how a function alters in relation to its independent variable. Modeling different real-world events from physics and engineering to biology and economics relies heavily on ODEs. Depending on the structure of the equation, they can be categorized as linear or non-linear and come in various orders. Now I'm gonna talk a little bit about the history of ODE. Mathematicians like Euler rigorously developed ODEs in the 17th and 18th century. Mathematicians like Cauchy made great advances and developed new concepts during the 19th century. And the prominence of numerical techniques and applications in science and engineering during the 20th century cemented ODE's significance in mathematical modeling. Here is the list of some of the methods of using ODE. Now we will discuss about the application of ODE for calculating the degradation rate of a radioactive isotope in nuclear industry by performing a real-life application where the decay process of that isotope can be described by a second-order homogeneous ODE. First of all, I will discuss a bit about the second-order homogeneous ODE, which is this equation, and it is a general form of linear homogeneous ODE. Here A represents the coefficient of the second derivative of yt with respect to time y double prime t. In the context of reaction processes, A reflects the rate of change in the rate of degradation. B represents the coefficient of the first derivative of yt with respect to time y prime t. In the context of reaction processes, B reflects the effect of factors that influence the degradation rate linearly with time. C represents the coefficient of yt itself. In the context of reaction processes, C reflects the intrinsic degradation rate. Now let's jump into the real-world example. The decay of radioactive isotope can be modeled by a second-order homogeneous differential equation. To quantify the process, scientists use the concept of the decay constant denoted by lambda. Let's use a specific radioactive isotope carbon-14 as an example. Its degradation process can be described by a second-order homogeneous ODE dN over dt equals to minus lambda times n. Separating the variables, we get the equation 1, and now integrating the both sides of equation 1, we get the equation 2, where c is the constant of integration. To solve for n, we will take the exponential of both sides, and then we will get the n, where k is a positive constant. N represents the number of radioactive atoms, lambda is the decay constant for C14, k is the initial number of radioactive atoms at t equals to 0. N equals to ke minus lambda t shows how the number of radioactive atoms decrease exponentially over time due to radioactive decay. Therefore, by solving this second-order homogeneous ODE, we can calculate the decay rate of C14. So that's all from me today. Thank you for hearing me out.